So good evening, everyone. For those of you who don't know me, my name is Bill Lee. I'm the chair of the OFA Marketing Working Group. I want to welcome you all to the 2016 OpenFabrics Alliance Workshop. If you've had a chance to take a look at the agenda, you'll notice that we have a very strong program in store for you this week. But tonight we start with a keynote talk, followed by a reception at the top floor of this hotel. Our keynote presenter tonight is Gary Grider. Gary is the leader of the High Performance Computing Division at Los Alamos National Labs. As division leader, Gary is responsible for all aspects of high performance computing technologies and deployment at Los Alamos. Gary is also the national co-coordinator for the U.S. Department of Energy, exascale storage, I/O, and data management. Gary has 30 active patents or applications in data storage area and has been working in HPC and HPC-related storage since 1984. Gary's talk tonight will cover the background that has brought us new storage tiers to the next generation of supercomputers and postulates what the economic crystal ball looks like for the coming decade. Further, he will suggest methods for leveraging HPC workflow studies to inform continued evolution of HPC storage hierarchy. Please join me in welcoming Gary to the podium.
Am I on? Yep. Thanks. So thank you very much for the kind intro. I haven't been to one of these since they were holding them up in Sonoma, so that's been a while. And I've been in computing for a long time, actually since 81, 84 at Los Alamos, and then 81 at Sandia, so long time inside the weapons complex. So I realize that I'm between you and the drinks, so I'll try to keep it in reasonable time. Quick set of old pictures because I like old pictures. You can see that we've been at this for a while, all the way from the 50s with Maniac and tubes all the way to today with this machine down here, Trinity, and our D-Wave machine, Ziggy. Anybody know why we called it Ziggy? There was a television program called Quantum Leap. Anybody old enough to remember that? And the computer in Quantum Leap was called Ziggy. Oh, well, we don't know yet, but I don't think you can hit it. We had to build an isolation platform for it, so no, you probably can't hit it. And we're also working on a 2020 machine called Crossroads that RFP will be out this summer. So a little bit of history. So back in 2007, 2008-ish, the exascale words were heating up, and we were trying to figure out, what would it take to get to an exascale. And by then, the goal was 2018, which is a pretty was a laudable goal, but we're certainly not going to make that. But that's why these numbers are 2018. But essentially, several of us were tasked with looking at the economics of how to get there, and I was tasked at looking at the storage economics because I'm an old storage guy, and of course, I'm a manager, thanks to a guy back there in the corner of the room. And so the tool of choice for managers is spreadsheets. And so that's what I used with spreadsheets. And I put together an economic model that took the machines that we were planning to buy inside the Department of Energy out to 2018, how big they would be, how much memory they would have, how unreliable they would be, therefore how fast we'd need to checkpoint the data out of them to get them to be able to behave themselves and run applications for 6 months at a time. So this is based on checkpoint restart. It was based on 2007-ish data, and it was guessing at what things would cost and how things would perform. And what that graph means up there is that if you were buying disk and only disk for this job, these are the amounts of dollars you would have to spend to buy disks in this time frame for the machines we were planning on buying. And I thought, I'm using spreadsheets, I'm an old manager, but I finally hit the big time because I had put millions of dollars on a log scale for the first time in my life. So I thought, there's the answer, right? I'm finally done, I can retire, but no, I'm not done yet. So the interesting thing about it is if you see this was an all flash guess, It's probably wrong now. In fact, all this data is wrong. This was an all-disk guess. And this was a hybrid guess, partly disk and partly flash or some other kind of solid state. And you can see that, since this is log scale, one of them, gets a lot cheaper. And in fact, there's this interesting crossover point. Now, of course, these dates are wrong because what we were planning on buying was elongated in time, but there's still a crossover that has happened, roughly about 2015 or so. And that is that we couldn't afford to buy disks for bandwidth because disks aren't priced for bandwidth. They're priced for capacity. And so this hybrid idea was born in 2008, 2009. It was first showed at this conference called the High-End Computing Interagency Working Group Conference in 2009. And the idea was you're going to need some tier of storage between you and your disk to be able to afford to do this going forward. At the same time, we also said, well, gosh, there's layers below disk that we have to worry about. We basically have a big tape archive. What's going to happen to that when we buy these big machines with these great big memory footprints in them? And that's what this model was. It's yet another spreadsheet. This spreadsheet goes back about 25 years. And it's basically how much does it cost to do parallel tape-oriented archiving. And over the last 20 years, at least, since I've been doing these sorts of models, the cost of archives for HPC systems or HPC centers has been basically equal to the amount of media you buy. Everything else is noise. The people, the robots, the servers, the network, everything is noise compared to the media. The media costs the most by far. Until such time as we started modeling this escapade to get off to exascale. And all of a sudden we see these two interesting years, 2015 and 2020, which is when we're going to buy a great big humongous machine that has multiple petabytes of main memory. And all of a sudden this red thing, new tape drives, started to cost a lot of money, right? You see the red never even entered into the equation until finally it did. And so what that meant was that this same driver, this bandwidth driver that we had up here that was causing us to buy flash instead of disk was causing us to not be able to afford tape to do the same job it was doing before. And so these two things were born in 2009, and it caused a bit of a ruckus. People didn't really know quite what to think of it. And it looks sort of like this logically. Before Trinity, the 2016 machine, this year's machine, the first machine with really a lot of memory, petabytes, this is what it looked like. Memory, maybe a couple of 100 terabytes of main memory in a supercomputer, parallel file system, maybe tens of petabytes or something like that, and archive, which we use our HPSS for the parallel archive. So that's what it looked like. This is what it looks like now. As of this year, we've added 2 tiers. That's what storage people do. That's the only thing we know how to do is add tiers. So that's what we did. We added tiers. We put this thing called a burst buffer in there. And the reason we put it in is purely driven by economics. Economics forced us to, we couldn't afford enough parallel file system to get the bandwidth that we needed. It was actually cheaper to put this layer of flash in. And so Trinity actually has one of these layers of flash. And so you've got memory up here. Memory is 2 petabytes on this machine. It gets overwritten continuously. The burst buffer is about 4 terabytes a second. It's about 4 petabytes, so it's about twice as big as memory. And it gets written every few hours, overwritten. Then with parallel file system, we still need one of those because this can't be big enough. So we needed to buy this for capacity and that for bandwidth. And that's about 1 terabyte a second, and it's about 100 petabytes on this machine. And then campaign storage was put in. Campaign storage is this idea that if you want to keep stuff around for a long time, but you don't have enough bandwidth down here in tape drives to be able to store that data for a while, you need to build more or less a disk-oriented archive and keep it in that for what we call a campaign. Campaign is a length of time that we study a piece of science. So it's a science campaign for us. And then That runs at about an order of magnitude less speed. It can get very, very large, maybe exabytes in size, and then the archive is still parallel tape, but it runs at yet an order of magnitude less. So that's the way our stack looks today. That's the way our stack looks last year. And the reason why is driven by those economic models that we did. So these burst buffer things that were predicted have showed up. And in fact, there are some out there you can go buy. So DataDirect has this thing called an infinite memory engine. That's a burst buffer. It's basically a burst buffer system. It's a write-through cache that's flash-based. It uses parallel log structures, just like the PLFS was back in 2007. And then it's underneath it sits disk. Cray has this thing called data warp. It's what we have on this Trinity machine. The Trinity machine is a Cray machine. And it's the same idea. It's a set of flash nodes that sit inside the machine that you burst to really fast, and then the data drains off to the disk drives, the parallel file system. EMC actually built another one, built one called ABBA. I forget what that stands for. Something burst buffer appliance, advanced burst buffer appliance. So anyway, you can go buy them. People are buying them. It's pretty young software, so don't expect it to work very well yet. Probably another year or two before it works pretty well, but the economics basically drove us to go do this. So burst buffers are out there. They're among us. You can buy them. What do they look like? They are mostly used for checkpoint restart today, although people are using them for analysis and other sorts of things. They're largely POSIX based today, so they look like a big file system. In fact, the Cray one, you basically say I want a job, and I want the job to have 1 million cores and 10,000 nodes or whatever. And oh, by the way, I'd like to have a petabyte of burst buffer, and it allocates that for you when your job launches. It preloads all the data up from the parallel file system that you tell it to onto this machine. Looks like a parallel file system, more or less. You work on it while it's on the burst buffer, and then occasionally you'll write these things out to disk. And then when you're done, it'll stage the stuff off if you tell it to. So that's what they look like today. This out-of-core business, people always thought, well, gosh, if you have burst buffers, why don't you use them both for parallel file system kind of activity and out-of-core kind of activity, meaning byte addressable, putting part of your application out there. And we thought that might happen back 2, 3, 4 years ago. It turns out it really didn't, and here's why, we think. There's this thing called HBM, high bandwidth memory, it's a fairly recent event. It's something that's come out recently. It's primarily an on-package memory, so it's not going through DIMMs, it's not going through copper to get there, it's going through parallel silicon to get there. So the bandwidths to it are more like, huge amounts. So they're like 500 to 1,000 gigabytes a second, like a terabyte a second, maybe even 2 terabytes a second to get data to and from these things, which is way, way faster than your stupid little DDR DIMMs, right? Those things are 50 gigabytes a second. You can get several of them, and maybe if you're lucky, you get going a couple hundred gigabytes a second, but that's if you're really lucky. And this other stuff, it's really interesting, right? So you've got this non-volatile store, whatever it is, flash or PCM or whatever, and it runs at this pathetic 2 gigabytes a second, which doesn't sound pathetic, but in memory land, it's pretty pathetic if you consider that we're talking about memories that run at 1 and 2 terabytes a second. And so before HBM, there was only about a 10x difference between this non-volatile store and DDR. However, because of this HBM, it's 2 orders of magnitude lower than where the applications are wanting to live. And so all of a sudden, it's starting to look like this non-volatile store isn't all that hot for working sets, at least for simulations. Certainly you can put read data in there if you're going to read it a fair amount, but not a lot. But not working set data that you're going to be updating every few microseconds. And so at any rate, we thought that this was going to have some out-of-core use, but I doubt it. Not in this time frame. Maybe later, but not right now, at least in simulation land. Campaign storage. So campaign storage systems are out there in the wild, and here's one of them we built. It's essentially the idea was, remember, if you go back to this slide, it sits right there. It's slower than the parallel file system, but way faster than parallel tape. It's to hold data for a few years during the period of science that you're trying to accomplish, not to hold data forever. But it's way longer than data that's flushed off of scratch file systems every month or so. But it's way bigger, and so than the parallel file system. So you need to figure out some really cheap way to do this. And if you're going to do it with disk, it's got to be really cheap disk. And how do you get a system to work real well with really cheap disk? Well, you ask the cloud people, because that's what they do. They use really cheap disk. They put neat erasure codes over them, and that's how they keep them up and alive. And so that's what we did. We said, gosh, let's steal, liberally from the cloud people. Let's take some cloud-oriented erasure code systems, and that can do 20 plus 4 or 40 plus 8 or whatever, a large number of resilience stripes, so that you can keep these things alive for reasonable periods of time, 2 years, and not lose any data, 3 years and so forth, and really build very large scalable systems in the exabyte range. So that's what we did, but the problem with that is our users don't know how to spell objects. We have literally $6 billion invested, that much, in our applications over the last 20 years. That much money invested in the weapons complexes, nuclear weapons, simulation applications. It's a lot of money. It's a big old freaking truck. It's going down the road really slowly, but it's really large. Figuring out how to change the vector of where that thing is headed is really hard. And so we needed to be able to put something that looked a little bit like POSIX on top of these objects to make them usable to a whole sea of legacy applications that are out there. And that's really true. I was at a conference last year, the IEEE Mass Storage conference that I get conned into helping with every year for some reason. And one of the things that they said, it was interesting. They had this panel, and the object guys were all up there, Scality and CleverSafe and SageWile, the Ceph guy, and all those guys were up there. And the first question was, how's business? And the answer was, business is great, double digit, everything is wonderful. We're selling these things like candy. This is, buy in, it's great, right? And the next question was, who are you selling them to, and what are they using them for? And the answer was, all new applications. All new web applications like Flickr and stuff like that, right, and Dropbox. And not us old, curmudgeony POSIX people. We can't figure out how to use them. And so it was interesting because there was this guy from United Healthcare. United Healthcare is this really big company. It's got a lot of IT. I mean, a truckload. They've got more robots than we do. And the guy stood up and said, I can't figure out how to use your crap because you don't have an interface that I can spell. I need something that looks a little bit like a file and something that looks a little bit like a folder, or my users can't figure out how to do it. And my applications can't figure out how to write to it. So we're not the only ones, but we're certainly involved here. So basically what we did is we said, well, let's figure out how to put a really, really super scalable namespace on top of these object stores to try to figure out how to use them to our advantage until such time, 10, 15 years from now, when our applications actually do move slightly to the left and start spelling object a little bit. And so that's what we did. We built this thing called MARFS. We looked at a lot of things because I hate writing software because it's hard to get right. Never get it right. We looked at a lot of things, all these things, to try to figure out if anything looked like a scalable namespace that would fit over an object store. And when I say scalable, I mean pretty scalable. 1 trillion objects in a file system, 1 billion objects in a directory, that kind of thing. With actual folders. And you can do LS, and you can do change mod, and all the crap you can do with POSIX file systems, right? And we couldn't find anything, so we started off writing one. It's out there, open source, so you can join if you want. A lot of people are looking at it right now. There was a pilot that was just run. It was 3 petabytes at about 3 gigabytes a second. Parallel file access. Single files in the range of up to about a petabyte right now is what we've tested. And then, of course, small files down to 0 bytes. And we're doing a demonstration this summer, scaling this thing out to show that it really scales. At any rate, there was a lot of real hard problems to solve. How do you figure out how to mesh object security and file system security, because they don't really mesh that well? How do you get things to scale this well, and so forth? So we think we're onto something. We think we've got something going here, but certainly we won't be the only ones, I'm sure. And if somebody else wants to come in and build a better one, I'll buy it instead of writing software. This is how it works a little bit. This is how it scales, at least. Scales in sort of what I'll call 3 dimensions. The metadata, this is interesting. It's the first time I've ever seen this. The metadata scales like sideways like this, and it breaks the trees down into multiple trees. This is very much like Parnassus or Lustre D&E1. And don't ask me any questions about Lustre because I'm the one that you can blame it on. That's kind of like Lustre D&E1. But the interesting thing about it is there's no file metadata in there. It's only directory metadata. So this is only storing relationships between files. It's not storing file metadata. File metadata is stored. File metadata is stored over here in shards separately. And the interesting thing about that is that when you scale the number of files across that way, and the number of directories across that way, and then the number of object systems that way, you end up with a pretty scalable system. But the fact that you've rearranged this and made the directory structure, the relationship data stored separately, is very interesting. It's very interesting because that's a graph. And it doesn't have to be a tree graph. It can be any shape graph. It doesn't matter. And in fact, that tree, those trees or those graphs don't have to even be stored in a file system. They can be stored in a triple store. It's a graph. It's entity relationship entity. It's a graph. And so that could be a set of scalable triple stores if you'd like. And that could be a set of scalable key value stores, right? Because that's flat data. There's no structure to it because the relationships are kept there. And so it's important because you could scale key value stores ad nausea. You know about those, right? They're out there by the dozen. And you can scale these pretty well too. And so it's interesting, right, that we basically converted POSIX into something that looks a little like what the data analytics world knows about and loves and breathes every day. And we've made it sit on top of these object stores in a pretty seamless way so that you can take advantage and leverage the cloud industry heavily. So, where's this all headed? We got these 5 layers, courtesy of, my stupid spreadsheets and the industry going along with it, right? For right or wrong. Where's it going? Well, we think it's probably not going to end up being 5 anymore. We think it's going to end up probably moving back to a smaller number. Why? Well, look at this tier, the IOPS bandwidth tier versus the burst buffer tier. The IOPS tier is really just saying, flash is going to get cheaper and cheaper. It's going to become more ubiquitous. Solid state storage is going to become more ubiquitous, and it's going to invade up into memory land. And we said that it already kind of is doing that in some cases. And it's going to invade down in the parallel file system land because it's going to get cheap enough that it can. The capacity tier, of course, it's already scalable in many, many ways. The namespace is probably more scalable than any file system that is out there today. In fact, it is already. And so it's going to invade up into the parallel file system tier, and of course it could invade down in the archive tier as well. That seems pretty much a no-brainer, and so we think that you'll end up with a capacity tier and an IOPS tier. Actually, EMC's coined a term already for this called 2 tiers. They even trademarked it, and I don't know why. But they obviously believe that this may happen, and And the reason that all this is true is because of economics and where things are headed and how things will mature and the like. But there's some interesting factoids over here, and these factoids are very interesting, I think. LANL's HPSS, our archive, is 53 petabytes, which is really not that big, but you know, it's kind of big for some people. And half or 500 million files and so forth. But look at this. Trinity is a supercomputer we just bought, and we're going to keep it for 5 years and throw it away, right? It's a supercomputer. They come and go. It's got 4 petabytes of flash and 100 petabytes of disk. And that's a scratch file system. So the scratch file system is twice as big as the archive. If you'd have told me this 25 years ago, I'd have never believed it. I never believed that we'd be buying systems that have in-system storage that's big or bigger than our archive. And then look at this 2020 machine in Crossroads. The thing may have 40 petabytes of in-system solid-state storage, flash or something like that, inside the machine. That's as big as our archive, in solid state, inside the machine, that we're going to throw away in 4 years. That's pretty amazing. So anyway, we never contemplate anything like that in the past, but this seems to be where we're headed. And it seems to be feasible at some point when all this economics works out. So we think that there'll be a compression of these tiers, and in fact this one may get squeezed out. And that's why I say this rest in peace parallel file system, because it may happen. So if this happens, if this dream happens of, gosh, what happens if this gets to be a bigger part of it and that gets to be a bigger part of it, then what would need to happen to make that occur? Well, the burst buffer idea would have to grow up a little bit, because today burst buffers aren't very reliable. They don't have to be very reliable. Remember, the durability of the data on those burst buffers is maybe a couple of hours, and then you're writing it off to disk. So, they can die. You don't have to RAID them. You don't have to protect them that much, because they can die. It's not a big deal to lose 2 hours. But if you're going to keep data out on the thing for 2 weeks or 2 months or something like that on this supercomputer, you're going to need to RAID it or erasure it or something. You're also going to need to protect the metadata for a much longer period of time, right? Because it has to be more robust. It has to run for longer. You've got to worry about quality of service, because you're going to have data on that machine that's not just for that job. You're going to have data on there for all kinds of jobs. And you're going to have to worry about quality of service that you've never had to worry about before. And you're going to have locality issues because of that. And so there's some things that have to happen to make this dream come true. There are people out there, believe it or not, already working on some of this stuff, because more than I believe that this sort of thing is going to happen. Probably some of it by 2020. What would need to happen to that capacity tier to make it really worthwhile and really be able to take the bottom end, the capacity part of the job fully? Probably the one thing that we're not too far along with, but it would need, is power managed disk. If you consider that you're going to take all this data and you're going to put it out on disk and you're going to leave it spinning, right now, the 100,000 drives that I have on the floor or whatever it is, something like that, is really a nit. It's not terribly a lot of power, maybe a megawatt, maybe 2. It's nothing compared to the site, because the site's way bigger than that. But that could change if you start keeping lots and lots and lots and lots of stuff on the disks. You could end up with lots of disks. Instead of 100,000, you could have 1 million, and all of a sudden I'd be spending 10 megawatts on power, and I'd be saying, hey, wait a minute, that's not so good. I'd rather do science with that instead of spinning those disks. So power managed disk is an important thing. You probably saw that Los Alamos just announced a credo with Seagate on this very topic of studying how we're going to meld power managed disk into this new concept. Power managed disks are not new. There was a company 20 years ago called Copan that built power managed disks, but it's been a while since anybody did this work, and so somebody needs to do it again. And of course the file count and the directory counts need to scale to ungodly numbers, and that the whole thing needs to mature, and there needs to be competitors out there. But it looks like this is all probably going to happen at some point fairly soon, within the next 6 to 8 years. Other considerations, so this is kind of interesting, right? So instead of, maybe someday we'll get rid of POSIX, or maybe someday we'll at least enhance it, right? Instead of writing files, which are just compressed, flattened forms of really nice structured data out of memory, instead of doing that, maybe we'll capture the structure. You know, that this data isn't unstructured, it's floating point values in arrays that are spread across machines that mean something. You know, it's a tetrahedral mesh with 50 floating point values per faceplate or something like that. And so it has structure. We're throwing that structure away today. You can't query it, you can't look at it. And we'd like to be able to store that and keep it. Why would we like to be able to store that and keep it and be able to look it up and figure out what's going on? Because we'd really like to be able to answer really hard questions that we can't answer today. An example is 6 years ago we ran a simulation, and we found out now, 6 years later, that it was based on some physics that was in that application 6 years ago that was just wrong. And we drew the wrong conclusion, and we went in front of the president and slammed our book on the table and said, the weapons are safe, they're going to work, no one's going to explode in Amarillo when they make one, you know, when they take it apart. And it turns out we were wrong. What do we do about that? How do we go figure out all the decisions we made associated with that simulation and try to go figure out how to correct that in the best possible way? Now, I'm not saying that happened, but that's the kind of question that we're trying to answer. We need to keep some provenance about this data. We need to keep some information about this data so that we can find this out. And it's really not terribly different than any other data analytics problem. It's just that we need to keep the damn data so that we can go look at it. And so we're hoping to get a whole lot more metadata out of these applications than we've gotten before and store it. And that's actually the whole reason why we're doing this DEOS project, one of the main reasons at least, with Intel and the Exascale project. The whole idea was, let's try to find a way to pry more metadata out of the applications to get it into the file, get it into the file system in some queryable way. And that, you can read about that project online. This is also kind of interesting, this concept of a loadable storage stack. So you might think that because you've got these tiers of storage, you've got, you know, flash, and then you've got disk, and then you've got tape or something like that. The obvious way to make that work and make everybody love it is to put an HSM on top of it. Well, turns out that may be kind of dumb. Putting an HSM on it kind of means typically that the highest level in the stack can see literally all the metadata. So it knows, it can't necessarily see all the data, but you could get on to the highest level of stack of an HSM today and say, I'd like to see this file, and it knows about that file, and it can go figure out how to get it staged back up to the highest tier. That's probably the last thing you want to do here. Probably you want to use something like the old AFS model, or like SVN, or whatever the Git for the young people, right? Sorry, I still have cards, you know. So you probably want to do something like when the job is submitted, you want it to provide a directory that you're going to go get a few billion metadata entries from, right? Probably a few billion, because we're talking about big machines. Have that loaded up in mass onto this high-level, performance tier. Have the objects start migrating up. They don't necessarily got to move up all of a sudden, but certainly the metadata could. And then you run when everything gets there. And you modify it as fast as you can possibly modify it, and you just beat the living crap out of this, online system. And then you're done. Your science is done, and you're happy, and you get, you want to go do something else. And the system is going to merge it all back in, and it's going to merge all that metadata back into the pristine copy of the metadata, which probably doesn't live up in the supercomputer. It probably lives in the capacity tier. So for the first time in really forever in HPC, the namespace is kept at the lower tier as opposed to at the upper tier, which is different. It's very much like AFS was years ago. Some of you may be AFS users. You used to be able to log. You used to be able to take your laptop on vacation and bring it back, and all the files you modified, it would sync them back into the file system you were using, kind of like Mail does today. Anyway, that may happen. There's actually some work going on in that space. We funded some work at CMU called IndexFS and BatchFS and DeltaFS, and that's what it was about, is could you check out massive amounts of, billions of entries of metadata, put them on a supercomputer, go have your way with them, and then have it all merged back together somehow magically. And probably the first thing that will happen is they'll reintroduce the concept of lost and found, and we'll finally have come full circle, and it'll be the 80s again. So that's probably enough about economics and predicting where the storage systems are going to go. How will this affect things? How will we decide this is going to affect things? How will we buy machines that are based on some of these concepts? How will this affect the business that I'm in? Well, inner workflows. So I've got an interesting story. I was at this workflow fest thingy that Lucy Noel, she's a Department of Energy program manager at Office of Science, and she was having this really big conference on workflows, and I got there and I sit down and I got my coffee and I listened to things, the presentations, and the first 3 presentations went by, and there were 3 people that got up there and said the word in situ and meant 3 different things by it. One meant in situ inside the job, one meant in situ inside the supercomputer, and one meant in situ inside the site. And the 3 things are pretty different. And so I got up, out of turn and said, Lucy, I'm confused. What's in situ mean? and when are you guys going to get a common language to talk to one another in, so that you don't confuse the rest of us? Because if you're confusing us, you're probably confusing each other. So I learned that. I also learned that there are probably more workflow tools out there to automate workflows than there are requirements documents to document them. And I also learned that I didn't really think that there was this common taxonomy for everybody to talk to one another about. And so I went on my merry way, listening to all these presentations and trying to figure out how I was going to use this information, it was actually a pretty good conference. It was just unfortunate that they hadn't worked on taxonomy so that they could understand one another well. And so I sort of went on my merry way, went back and started working on ordering this 2020 supercomputer that's from this Apex organization, which is Los Alamos, Sandia, and NERSC. And I sat through all these meetings, and the vendors, they'd come in and they'd say, where do you want your flash? And where do you want your SCM? And where do you want it put? And how big do you want it to be? And do you want it to be near the disk, or do you want it to be near the computer, or do you want it to be in the network? And how much do you want? And how fast do you want each piece to be? And I finally had enough of that, and I said, you know what? I don't think you want me to tell you where to put your stupid NAND and your stupid, I don't care. I honestly don't care where you put it. What I'm trying to do is I'm trying to figure out how to do a science workflow and get the most science through this machine in 6 months. And I don't care where you put the flash. I really want you to tell me where to put the flash, because you understand how much it's going to cost and where you can put it economically and your software stack and all that stuff. So I decided right then and there that this procurement, this 2020 procurement, would be the first procurement DOE's ever had that procured a supercomputer based on workflows, trying to get the most science through the machine in 6 months, instead of specific, this has got to go 50 gigabytes a second, and that's got to go 75 gigabytes a second, and so forth. And so that's what I set about doing. This was my first incantation of how to do that. You've got a science campaign, and you've got application development and setup and store and analyze and experiment and the simulation that runs and so forth. And each one you need some volume and velocity information and sizes and things like that. And I decided, well, that's not quite it. Let's move forward to the next one. The next one was really went round the bend too far, and that was, look, this is interesting, right? So the further away you get further up you go, that's how often the thing gets changed or overwritten. How big it is the size of the data. How big the line is how fast it goes. The color of it is all this, how long do you got to keep it? This has got to stay around forever, and that's got to stay around for seconds, and so forth. It was kind of interesting, right? It was a good taxonomy, and it was an exercise in taxonomy, and that's about all it turned out to be. But it helped people because they started thinking about it, saying, gosh, you know, if we could describe our science that we're trying to accomplish in this way, in some way that's similar to this, we could give this to the vendors along with the specs, you know, and you get $250 million if you win, and maybe we'd get more science out of the machines this way. So it went to there, and then it moved on to how are we actually going to do this? This is buying this 2020 machine with this Apex organization, Los Alamos, Sandia, and NERSC. And if you remember back, you may not know this, Trinity, which was our last machine that's being put in now, was one of the first machines that we didn't specify flops. We said, we got these 6 applications, and we need to run them 8 times faster than we ran them before, or 8 times bigger than we ran them before, or whatever. And we didn't care about flops. It didn't really matter. We just had these applications. We needed them to run 8 times bigger, faster. And for the first time, the vendors didn't see flops, and they were confused. And they said, what do? I don't know how many flops to give you. And I said, I don't care how many flops you give me. I don't want to count them. I don't want to run a linpack. If you want to run a linpack, go for it, but I don't care. I want to run these apps, and I want to run them faster and bigger. And they hated it for a while until they realized, oh, that's pretty cool. That's a tool. We can use that. We can optimize with that. We also said we wanted to go forward 90% of the time. What do I mean by that? Well, applications have to checkpoint, right? And they're not going forward when they're checkpointing, and they're not going forward when they're restoring. They're going forward when they're calculating. So checkpoint restart is a necessary evil. I don't want to do it. But basically we said we want the thing to go forward 90% of the time. And then they said, well, won't you tell me how many gigabytes per second you want? And I said, no, I don't care about how many gigabytes per second. I care about going forward 90% of the time. If you can make a machine that runs 90% of the time without any failure, I don't want to buy any disks. I don't need them. But of course they can't do that. So anyway, they didn't like it at first, but they basically figured out, gosh, looks like you need burst buffers and so forth, and they came to like it. So we did the same thing with this current procurement. No flops still. We don't care. We're just going to take the applications we have now, we're going to run them bigger and faster. We still want it to go forward a large percentage of the time. But then the next question was, okay, what about all this? Where do you put your flash and all that? And we said, we don't care. We're going to publish some workflows, and we're going to tell you how many of those we run and how often we run them and the mix that we run them. And you tell me what machine to buy. And you convince me that your machine is better than the guy next to your's machine for running the most number of those science applications through that machine in 6 months or something. And that resulted in this. And we finally got somebody besides a manager involved in doing this work. There was a team of people that looked at all the applications running at all these sites. And they came up with 3 levels of workflow. One was a level of workflow happening in the kernel of a compute. One was at the application level. And one was like this at the high level, where each one of these things is an application or the part of an application. So there's 3 levels of workflow for each application. And then there's this same idea of you keep it forever, you don't keep it for very long, and so forth. And how you go do this. This is a simulation science pipeline. And they did it for several different applications. And lo and behold, they only found 2 types of workflows. This one and that one. And this one matched a UQ science pipeline. A UQ science pipeline is where we do a lot of statistics to try to figure out whether we got the right answer or not. And oftentimes those happen in things called ensembles. Ensembles, instead of launching one big ass job that runs on the whole computer for 6 months, which is what that one is, instead this one is an ensemble. And an ensemble is launch a whole crap load of little bitty jobs. They may only take 4 nodes each, but you're running a million of them, and you're looking at statistics and you're trying to figure out whether you're getting the right answer or not. And it also matched pretty well like a telescope or an accelerator providing data that turns out to look an awful lot like ensembles. And so basically we ended up with these 2 types of workflows, simulation and UQ ensemble. And we went and got our applications. EAP and LAP and Silverton and VPIC for LANL and Sandia and some stuff for Livermore and some stuff for NERSC. And what's interesting right here is it's what kind of workflow is it, right? Is it a HTC or is it a SIM or is it something else? What percentage of that workflow makes up this machine we're going to buy? So what this means is that simulation eats 60% of the machine I'm about to buy. That thing, not the application itself, but that science, reading the data in, calculating, writing the data out, doing checkpoints, all that crap. So this table was generated, and in fact there's a white paper that you can download with the draft RFP for this machine that has this stuff in gory detail about how this is going to work. And again, this is a grand experiment. We hope it works, but we think we're going to end up being able to compare vendors' machines far better than we have in the past using this method. And again, the vendors hated it at first because they went, oh crap, tell me how many megabytes per second you want. And we don't have it in there. It's not in the RFP. Anyway, so that's what that is. So in summary, so that you can get to drinks pretty soon, economic modeling, you know, in the stupid little managerial spreadsheets that were produced in 2008, 2009 were a pretty interesting tool, right? They predicted where industry was going to go. Maybe they even told industry where to go. You see these burst buffers, you see these RFS kind of things that are happening. And I don't know that they would have happened without that, but they probably would have because, you know, economics would have forced us into those solutions. But at least they recognized way out front you needed these things. So I would argue that we need more economic modeling going forward to predict these you know, turns in the road that we're going to have. I would also argue that given that the footprint of everything but computing is growing so tremendously. In 1996, we bought a machine called Blue Mountain. Blue Mountain was like $70 million, and we spent $3 million on everything, the storage, the network, the pipes, the copper, everything. So it was like 4% or something. And now it's 40%. I put in $27 million worth of 36-inch water pipes to cool this stupid Trinity machine. We ever tried to cool 33 megawatts? It's a big bunch of water. And so I would argue that because that stuff is becoming so large, such a large percentage of running a center, that this idea of workflow needs to become very, very important in buying these things, because you're no longer buying compute, you're buying all the stuff, and the compute's almost coming for free. And that combining those things, economics and workflows, actually turns out to be a pretty useful thing and has served us pretty well, I think. So anyway, that's it. That's not a picture of Steve Poole. But he was probably at the lab at that time. Maybe not. You were probably at Cray at that time. Any questions anybody's got for me? Or should the old storage guy just exit stage left and get to the drinks? Yeah.
So how do you see archive going away? I mean, that would be a culture shift, because you have to convince people not to save everything.
That's an excellent question. So I don't see archive going away at all. In fact, I don't see tape going away. And the reason I don't see tape going away, just to answer this question first, because I want to, there's times when you want it to be slow on purpose. In fact, there's times you want it to be damn slow on purpose. Why? Because of insider threats. Right? If I put all my data on something that goes hundreds of gigabytes a second, I can delete it at hundreds of gigabytes a second. Talk about your, denial of service, man, you can kill yourself, right? And so you really need to provide a safe place for these people to store results where that's not going to happen. And tape is perfect for that, because no matter how hard you try, you can't get that shit to go fast. You can do it. Even if you do it in parallel, you still can't go very fast. And so I don't see tape going away. Archive, and how do we convince people to use archive correctly, is interesting. And I think that our premise, and it's just a premise, is that we're going to give people a lot of storage for the length of their campaign, and maybe even for a year after, and let them do analysis and try to figure out what's worth saving. And then we're going to give them a tiny little straw, just like we have today, to the archive, and we're going to say, you only get to store this much. So pick out the gems, keep all the metadata, and if you have to, rerun it. Will they accept it? I don't know, but economically we have no choice. They have to go there. We think we're giving them a good tool with this campaign thing so they can keep data, really large amounts of data around with high bandwidth for years. But it's a cultural question, so ask somebody younger. Steve.
So you didn't mention about RFS. I'm assuming it's user space, because one of the problems that we've had in our environment is Lustre is so kernel intensive, and in order to do anything in the kernel in my environment, you cannot take that many polygraph tests.
So I spent every Thursday in my life for 6 years with Peter Brahm, arguing why we should not have all this stuff in the kernel. It didn't work out so well for me, did it? Don't have any hair or anything. Peter's a smart guy. He's a great guy. Yes, it's completely user space. We made sure that I couldn't deal with the same problem, only not as bad as yours, but yes, it's completely user space. In fact, the demonstration we're going to run is quite interesting. Remember I told you back here that I had this metadata thing, and it scales 3 different ways. It's interesting because there's an API in this system to plug in any kind of directory relationship holder you'd like. So if you want to plug in a file system, peachy. If you want to plug in a triple store, peachy. Just write yourself a little shim and there you go. And it parallelizes across them automatically. If you want to run the key value stores underneath that metadata, fine. If you want to put file systems on that metadata, fine. You just write yourself a little shim and presto, you have it. And then of course this is all just libaws curl crap, so it's just completely user space, written by junior high kids, and we're using it. It's interesting, right? So we're going to actually do a demonstration. I think I'm going to take Cielo, which is our last supercomputer that's going to be shut down in July, and basically run all this on a supercomputer. It's not really designed to run on a supercomputer. It's just designed to run in user space anywhere. You can use a supercomputer. And that's where we're going to do this trillion file, billion file in a directory demonstration on a supercomputer, and essentially set these things up as key value stores. In fact, we'll probably use this thing called MDHIM that we built a while back that the DoD helped pay for, that is basically a parallelization of the key value store. And then we'll probably end up using OrangeFS here, because OrangeFS is user space, and it does directory attribute caching, which turns out to be useful in this case. And so, yeah, it's all user space. The demonstration will be all user space. You'll be able to submit a job and run this thing as user, and have a user space instantiated trillion file system thingy in memory for you. That's the idea. Everybody's thirsty.
I think you touched on it very well. The problem that we're facing, and Susan really hit the nail on the head, discussing what percentage of on-package memory versus what package of flash that we have in the systems really kind of depends on if we push this cultural shift well or not, right? We continue to build systems that allow the users to create data and store all of it, right? We do massive parametric studies, right, and save everything, right? If we're successful in creating this cultural shift that gets users to instead weed out what's important in flight and save only that, that really determines kind of what percentage we have in each one of those tiers, right? So it's a bit incumbent upon us to make that cultural shift, because I don't know if you agree or not. I think that we simply won't be able to power the storage to save all this in 5 to 7 years, right?
It is all economics, literally, and culture. It's not really so much technology, although getting software right is hard, but yes, it's all economics and culture and how those two mix. And you know, it's a sea change. Los Alamos, when I went to work for Los Alamos some ungodly number of years ago, we were told save everything. It's cheap. It's way cheaper than your time. It's way cheaper than any, you know, just save it all. Hit the button. We had this thing called CFS. It would save files, and we still have files from CFS. It was great. And so, you know, a third of the people at the lab grew up there. They just want to hit the save button and not worry about it. And we can't afford that anymore. We'll see. Luckily, I'll retire in a few years when I run out of cards, and it'll be Susan's problem.
All right. Thank you very much.
Thank you.